Assalamu alaikum class, ninth lecture, a course relating to the statistical inference and topic will be Lehman, sheffs theorem and the generalization of Rao-Blackwell theorem. As we in statistical inference are dealing with the point estimation and basically estimation, and then the point estimation, we are going through the qualities of a point estimation, and in which we have seen unbiasedness, sufficiency, efficiency, completeness, and then we, after finding the point estimator, sometimes we are unable to find the best point estimator. Then we have other methods, that are the method of movements and the method of maximum likelihood and the method of least square. In our previous lectures, last two lectures, we have gone through the maximum likelihood estimators and the method of movements. This Lehman Sheff theorems was left from the sufficiency and generalization of the Rho-Blackwell theorem from the K-parametric space. So today we will try to go through these two topics. If we see the Lehman Sheff's theorem, it is basically the try to combine all the qualities of the point estimator into the one formula, or one at one point. It's if we define what is the idea behind the Lehman-Sheffs theorem, so we can say that if we suppose that y is a sufficient statistic for theta, and we say that y is complete if there are no non-trivial unbiased estimates of 0 based on y, and if expected of gy is equal to 0 for all theta, then p theta gy is equal to 0 is equal to 1 for all theta. Thus, if we have two unbiased estimates of theta based on y, say some phi of y and some psi of y, and then expected of phi of y minus psi of y is equal to 0 for all theta, so that regardless of theta, phi y and psi y coincide with probability 1. So if we find one unbiased estimate of theta based on y, we have essentially found all of them. So this idea is behind the Lehman-Sheffs theorem. So your statement is that x random variable x1 up to xn be a random sample from the PDF or PF f of x theta if s is equal to s of x1 up to xn is a complete sufficient statistic, and if t star is equal to t star of s is a function of s is an unbiased estimator of g of theta, then t star is an minimum variance unbiased estimator of g of theta. So its proof is let t prime be another unbiased estimator of g of theta, which is a function of s. Then that is t prime t of s, then expected of t star minus t prime is equal to 0 for theta belonging the parameter space, and t star minus t is a function of s. So by completeness of s, probability of t star s and t prime s is equal to 0 is equal to 1 for all theta belonging to the parametric space. Hence, there is only one unbiased estimator of g of theta, that is a function of s. Now let t be an unbiased estimator of g theta, and since expected of t by s is an unbiased estimator of g of theta depending on s, by Rao-Blackwell theorem, t star is equal to expected of t given s, and variance of t star is less than equal to variance of t for all theta belonging to sample space. Hence, t star is an minimum variance unbiased estimator. So in this way, this theorem says two different things. That first is, if a complete sufficient statistic x exists, and if there is an unbiased estimator of g of theta, then there is an uniformly minimum variance unbiased estimator for g of theta. And second thing is, if uniformly minimum variance unbiased estimator is the unique unbiased estimator of g of theta, then is a function of s. To actually find that unbiased estimator of g of theta, which is a function of s, we have the following three methods. First is simply guess the correct form of the function of s that defines the desired estimator. Second is to guess or find any unbiased estimator of g of theta and then calculate the conditional expectation of the unbiased estimator when the complete sufficient statistic. Or third is to solve for t star dot is the equation expected of t star s is equal to g of theta. That is solve integration t star s f of s d of s is equal to g of theta is the case of continuous random variables, or sum of t star s f of x is equal to g of theta for s is a discrete random variable case. We imply these methods in the following examples, and these three strings are in the Lehman sheffs theorem, so we will try to uh, prove it, and uh, we'll also see in some examples through with the help of some examples how to prove this, that for example the example that is on the slide is that x1 up to xn be a random sample from the Poisson distribution. So we will find a uniformly minimum variance and biased estimator of lambda and E of lambda. So we also try to find out its mean and variances. So, and also we will use to find out the minimum variance and biased estimator for the PDF of theta e power minus x minus theta x I 0 to infinity x, and also other examples relating to some continuous or some discrete distributions. Also, we can use the Poisson distribution and the negative binomial distribution and other discrete distribution, just as the Cauchy distribution, and complete sufficient statistic for the exponential cases we will also consider. This all is relating to the Lehman-Sheffs theorem. So if we see to the vector of parameters, then under this topic, we will assume that x be the random samples from the PDF of f of x theta 1 up to theta k, where parameter theta is equal to theta 1 up to theta k and parameter space star are k dimensional. We want to simultaneously estimate g1 theta up till gr theta, where j theta is equal to j varying from 1 till r is some function of theta. Theta is equal to theta 1 up to theta k. A point estimator of g1 theta is equal to gr of theta is a vector of a statistic, say t1 up to tr, where tj is equal to tj of x1 up to xn, and tj is an estimator of gj theta. We will consider only unbiased estimator and look for our best estimator within the discrete class of the unbiased estimator. This is the example of unbiased estimator of g1 theta up to g or of theta if and only if expected of tj is equal to g of j theta for j varying from 1 till r and for all theta belonging to the sample space. Previously, while considering unbiased estimator of real valued function g of theta, we implied the variance of an estimator as a measure of its closeness to the statistic g of theta. We generally generalize the concept of variance to r dimensional vector of variance for the unbiased estimators t1 up to tr. So, and we'll find the matrix whose jth element is sigma ij theta, and that matrix will be called the covariance matrix of the estimator T1 up to TR. And on the same line, we then define the generalized variance, and that variance it calls Wilks generalized variance. We also go through the generalization of Black-Well-Raw theorem, and that is the theorem is about x1 up to xn random samples from the PDF f of x theta 1 up to theta k, and we consider s1 of x1 up to xn, and sm is equal to sm x1 up to xn be a set of jointly sufficient statistic, and let t1 up to tr be the unbiased estimator of g1 theta up to gr theta. Then we define tj prime that will be equal to expected of tj when s1 up to sm sufficient statistic are given, and j varying from 1 till r, then we have three cases. First is that t1 prime up to tr prime is a statistic and an unbiased estimator of g1 theta up till gr theta, and tj prime is equal to tj prime s1 up to sm, that is tj prime is a function of the sufficient statistic s1 up to sn, where j varying from 1 till r. The second option is that variance of tj prime will be less than or equal to variance of tj for every theta belonging to the parametric space, and j varying from 1 till r. And third is Wilks generalized variance of t1 prime up to tr prime is smaller than Wilks generalized variance of t1 up to tr. So this is the case when we generalize the Rao-Blackwell theorem, and that gives us the Wilks generalized variance. We will also go through the concept of joint completeness. That is that we have the x1 up to xn random samples from the PDF of x theta 1 up to theta k, and we have the statistic t1 up to tn and t1 up to tm are defined to be jointly complete if and only if expected of z t1 up to tm is equal to 0 for theta belonging to the parametric space applies that the probability of z t1 up to tm is equal to 0 is 1 for all theta belonging to the parameter space, and where z t1 up to tm is a statistic. So we will also go through some examples relating to this generalized variance and generalization of Rao-Blackwell theorem. Examples will relate to some PDFs of some uh, discrete distributions or some continuous distributions. So this all we will try to go through in our lecture 9, and we will also go through the generalization of Lehman theorems. So this in a application, this theorem is very useful as it gives us the generalization of the variances, and it also tries to put all the points of a good point estimator in one statement, in one theorem, in one idea. So all we will go through inshallah in the class. So till then class, this video I am sure will help you to understand the concept and the idea that is behind the lecture 9, that is about the Lehman-Sheffs theorem and its generalization, Rao-Blackwell theorem's generalization, and also the Wilks generalized variance. Till then, thank you. Khuda Hafiz. Take care.